Dear students, in this video we will talk about pinacol-pinacolone rearrangement. And pinacol-pinacolone rearrangement was first proposed by Rudolf Wilhelm Fittig. Rudolf Fittig was working on certain derivatives of acetone. He published the article whose title was Certain Derivatives of Acetone. And journal name was Liebig's Annalen der Chemie. And year of publication was 1860. So in this rearrangement, 1,2-diols or vicinal diols or glycols, they are converted in the presence of acid to corresponding carbonyl compound, aldehyde or ketone, and the equation would be this is pinacol and it converts in the presence of 25% sulfuric acid, cold sulfuric acid, and it converts into pinacolone. So this is the general chemical equation for this rearrangement, and now we see the mechanism. In the first step, we add acid, or we can simply write H plus. So both of these hydroxyl groups are identical, therefore this molecule is symmetrical. Any one of them can be protonated. As a result of protonation, we get positive charge on oxygen, which is not acceptable for an electronegative atom like oxygen. As a result, water molecule would be eliminated and it would take electron pair with it, and we will get a carbocation. So this is a tertiary carbocation. Now main driving force of this reaction is this carbocation pulls a substituent from this carbon attached to this carbon, and a lone pair pushes the group to migrate, and as a result of this push and pull mechanism, we get the migration, and this is obtained. Another major reason for this rearrangement is the complete octet of this group, because here octet is not complete, however here octet is complete, therefore migration can occur and rearrangement takes place, and in the end proton is removed and we get pinacolone. So I can explain once again. In this reaction, two hydroxyl groups are identical, so therefore one of them can be protonated with the acid which is being used as catalyst, and as a result of protonation we get OH2 here, and oxygen gets positive charge, because when in neutral state one atom gives away the electrons, it gets positive charge. So as a result we get OH2 positive here, which is eliminated because oxygen, being the electronegative atom, does not like positive charge on it, and we get the tertiary carbocation. Now as a result of push and pull mechanism, because this is pulling the substituent toward itself, and here oxygen is pushing the substituent, therefore we get the rearrangement here. So 1,2 rearrangement, it occurs here, and in the last step proton is eliminated and we get pinacolone as product. So there are certain features of this rearrangement. Regarding the conversion of pinacol to pinacolone, first feature is this is acid catalyzed. It can be catalyzed by mineral acid such as sulfuric acid 25% in cold state, and concentrated acid is avoided because of the possible loss of water molecules, and eventually we can get butadiene. Therefore sulfuric acid in 25% concentration is used, and Lewis acids can also be used. For example, BF3, boron trifluoride diethyl etherate, can also be used. And if all four substituents they are identical, we get only one product. So only one product is obtained if all four substituents are identical. Otherwise we get mixture of products. Next point is this reaction is regioselective. And regioselectivity, it depends on relative migratory aptitude. From the mechanism we saw that the substituent which migrated took its electron pair along with. So the substituent which tends to stabilize the carbocation better would be migrated in preference. So the substituent which is better electron donor would be migrated preferentially. So better electron donor migrates preferentially. Now, any cyclic or acyclic vicinal diol can undergo this reaction. In case of cyclic substrates, there is possibility of ring expansion or ring contraction during rearrangement. Now we see the migratory aptitude. The relative migratory aptitude is aryl comparable to hydride, which is comparable to vinyl or alkenyl, and these systems have better migratory aptitude to alkyl systems, and better is among them is tertiabutyl, cyclopropyl, secondary to primary. So this is the relative migratory aptitude for pinacol-pinacolone rearrangement. And now we see some examples. If we have a compound like this, then we have two different hydroxyl groups. Now we have to see which of them would be protonated when treated with acid. Here we have the possibility to protonate this hydroxyl group. So if we protonate this one, we get this. And here water loss would take place, and we would get this carbocation. And if protonation takes place at this hydroxyl group, we would get this one, and after the loss of water molecule, we would get this carbocation. So among these two, we have to see which one is more stable. So hydroxyl group among the two would be, that hydroxyl group among the two would be protonated, which leaves behind a stable carbocation. And here we can see we have two phenyl groups to stabilize this benzylic carbocation, and here we have only one phenyl group. So this is more stable as compared to this one. So this route will be followed, and as a result, we will get the migration of phenyl group. And why we get phenyl migrated? Because among phenyl and methyl, we have just seen that aryl groups have better migration ability as compared to alkyl groups, and also phenyl is better electron donor as compared to methyl group. So therefore we will get this molecule, and which upon loss of proton would give this. So I hope this example is clear to you, and we see some more examples. Another example would be this one, and here again we have two hydroxyl groups, and we have the question which would be protonated. Now just I have discussed that any hydroxyl group which when leaves as water molecule after protonation and produces a stable carbocation would be protonated. So if this is protonated, it would leave behind a carbocation which would be stabilized by these two phenyl groups. Therefore this would be protonated in preference, because here we have methyl groups and they are not better than phenyl groups to stabilize the resulting carbocation. That's why we get this one, and water molecule would be eliminated, and we would get this carbocation, and again push and pull mechanism, and we will get this molecule, which upon loss of proton would result in our target molecule. Now we see an example for the cyclic substrates. So we have this diol, and we want to protonate it, because in this case we have symmetrical diol, so any one of them would be protonated, and as a result we would get this. And here water molecule would be eliminated, so we would get this carbocation. Here again this lone pair would come here, and one of the groups would migrate here, and we would get this one. Now we have to see how we have formed this. When we have the problem of complex molecules, it's better to number the carbon. For example, we number it 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Now this hydroxyl group which is converting into the carbonyl compound is present on carbon 1. So this is carbon 1. Carbon 1 is joined by 2, 3, 4, 5, and 5 has now joined 6. So it is attached to 6. It is no more attached to 1. So 5 is no more attached to 1. It is attached to now 6, and 6 is now attached to 7, 8, 9 and 10. So we have got ring expansion here, because this 5-membered ring has expanded and convert it into 6-membered ring. So this is the 6-membered ring. And to make this structure drawing easier, one crude method would be, because this arrow tail shows here that this bond is breaking and making connection here, so we break this bond and we join this here. So now we can see this is 1 2 3 4 5 6 membered, and 6 is the carbon atom which is joining both the rings. Here we have also 6 carbon joining both the rings. So this is the example of spiro compounds. So after loss of proton, we will get this spiro molecule. So this is the example of cyclic substrates involving pinacol-pinacolone rearrangement. So I hope this is clear to you. A very similar rearrangement can take place when we don't have both the hydroxyl group, rather we have a leaving group here. This rearrangement is called semi-pinacol rearrangement. In this rearrangement, we have a leaving group here instead of another hydroxyl group, and this X can be chlorine, bromine, and 2 positive, SR, OMS, methyl, OTS, tosylate, and under mild conditions this would be eliminated and we would get this carbocation. So X would be eliminated, and again we will have same mechanism, and any one of them which is better at migration or better electron donor would migrate, and we would get this molecule, and proton would be eliminated and corresponding compound would be formed. This semi-pinacol rearrangement is also named as Tikhonov-Demjanov rearrangement. On the name of the scientist. So I hope you have completely understood about pinacol-pinacolone rearrangement, and if you find any confusion or question regarding the lecture today, leave your comments in comment box. Thanks.